Salam and welcome everyone. So today we're going to be working on the question on the screen that says evaluate the linear momentum and kinetic energy of a free electron described by the wave function e raised to the power of ikx with k equals 3 nanometers raised to the power of negative 1. So anytime you have a question like this, by the way, this question is from the Atkins Physical Chemistry 11th edition textbook, and this is from chapter 7D, where we study translational motion. So, or basically translational motion of electrons. So, evaluate the linear momentum and kinetic energy of a free electron described by the wave function e raised to the power of ikx with k equal 3 nanometer raised to the power of negative 1. So we are asked to evaluate, basically solve for the linear momentum as well as the kinetic energy. So we have to write out the parameters. So we are asked to solve for E sub k, which is the kinetic energy, we don't know what that is, as well as p, which is the linear momentum, we don't know what that is, of a free electron described by the wave function. We've been told the wave function is equal to wave function e raised to the power of ikx and the value of k to be 3 nanometer raised to the power of negative 1, or we can just say 3 times 1 over nanometer. Basically, the unit of k is 1 over nanometer. Anyways, I just wanted to make sure no one is confused by this. So yeah, that's basically it. So when you're given a question like this, the first thing you have to note is that we're told that we're dealing with a free electron here. That's the main keyword that we need. And we also told the wave function e raised to the power of ikx. From the knowledge of the keywords and all the other things that were shown, we're supposed to use this formula. And this is the formula for free motion in one dimension. It is the wave function of x is equal to a e raised to the power of ikx plus b e raised to the power of negative ikx. Okay. So this formula right here is free motion formula in one dimension. So that's it, where a e raised to the power of ikx, okay, is the particle, okay, with linear momentum, okay? You see all of this in your textbook, by the way. Positive k h. So basically k, and then there's a slash on top of it. So basically the Planck's constant divided, sorry, with a slash on top of it, and you have a different value. So the value for this is no longer going to be 6.626 times 10 to the power of negative 34 joule seconds anymore. It's going to be a complete different value. And then, of course, b e to the negative ikx is the particle with linear momentum negative k slash, sorry, negative kh slash. So anyways, I wanted to quickly mention something just so no one is confused. I wanted to quickly mention that I'm saying all of this information and the concepts so everybody is on the same page. We're told already what the wave function is. That means we're going to note that all this is basically going to equal to 0. So this is basically the wave function that we're dealing with. You can ignore a. A is just simply a constant. In this case, they just told us the wave function is equal to e raised to the power of ikx. So we can just assume the value of a is 1. I also wanted to mention that we can think about linear momentum, we're getting a positive or a negative value. It's just simply the fact that the electron that we're dealing with here, whenever you have a positive k slash h, basically whenever the linear momentum is positive, in this case positive k h slash, right, that means the electron is traveling to the right, and whenever the electron is traveling to the left, we end up with negative kh slash, which is the particle with linear momentum when the particle is going to the left direction. So that's it. The linear momentum is actually the value in of itself, while the positive and the negative is telling us whether it's going to the left side or to the right side. So that's it. Yeah. So if it's positive, it's going to the right side. If it's negative, it's going to the left side. That's it. That's literally it. So the linear momentum is just simply P is equal to positive KH slash. So that's literally it. This is the formula we're going to use to solve for that. So now that we know that, we know what our K is Our K is simply 3 divided by nanometers, okay, or 3 nanometer raised to the power of -1. And then our H slash is also a constant value. By the way, some of you who basically don't know what H slash is just Planck's constant divided by something else. So that's basically, I can't remember what it is right now. And maybe before the end of this video, I'm going to tell you. But it's different from the Planck's constant H. H slash is different from the Planck's constant H. And H slash has the value um, 1.05 46 times 10 raised to the power of -34 joules seconds. So that is basically the value here. So all we have to do is simply substitute. So P is equal to positive 3, okay, divided by nanometers. So nanometers is just the same thing as 1 times 10 raised to the power of -9 meters, okay, times H slash, which is just 1.0546 times 10 raised to the power of -34 joules seconds. Now we've run into an issue here. We see that we cannot cancel any of the information out simply because we have joules here and we have meters. So we're going to make sure we break down the units joules and convert it into SI units. Remember, this is just a side note here. Remember, joules is the unit for energy, right? And energy is just simply force times distance, okay? And then force can also be broken down to mean mass times acceleration. So basically, mass times acceleration times distance is what energy is. So when we want to break this down, we see that joules is going to equal the units of each one of this. The units for mass is kilograms. The unit for acceleration is meter per second squared. And the unit for distance is just simply meter. So joules is just simply kilogram meter squared per second squared. So we're going to rewrite our work in terms of kilogram meter squared per second squared so that we can properly use the units that we need to solve this question. So we have P, the linear momentum, is just simply positive. I don't have to write that down. 3 divided by 1 times 10 raised to the power of -9 meters. Don't forget, 1 over nanometers is the unit for K. Yeah, so that is it. So 3 divided by 1 over 10 raised to the power of -9, multiplied by 1.0546 times 10 raised to the power of -34. Joules is just simply kilogram meter squared per second squared. But let's not forget that it's not just joules that we're dealing with. We also have seconds here. So joule seconds. So let's just say multiply by seconds. If you're the one person who loves to do math, this is going to be like easy for you. But for those of you who don't understand, kilogram meter square per second square is what I already explained to you. The SI unit for joules is, the SI unit for energy is. This second is just for us to remember that when we're dealing with this H slash, our unit is joule second. So even though we have kilogram meter squared per second squared, we also have to not forget that there's actually an seconds that's part of the units there. So of course, let us cancel out any units. So we can cancel out seconds here, cancel out seconds here, cancel out mass here, cancel out mass here. So P ends up becoming 3 divided by 1 times 10 raised to the power of -9, which is just the same thing as 3 times 10 raised to the power of 9, okay, multiplied by 1.0546 times 10 raised to the power of -34 kilogram meter per second. So you're going to input all of this information in the calculator. We end up getting the linear momentum to be P is equal to 3.1638 times 10 raised to the power of -25 kilogram meter per second. Now, I want to quickly mention something to you guys. Anytime you're given a question in chemistry, physics, and basically a calculation question, you have to make sure you're putting your work in the proper number of sig figs. We can see that we've been given the raw value or we've solved for the raw value here, but we have to put in the proper number of significant figures. So we go back to our question. We see that we're only given one information and it is in one significant figure. So our final answer is going to be rounded up to one significant figure. So the answer will end up being the value for linear momentum P is simply 3 times 10 raised to the power of negative 25 kilogram meter per second. So that is basically the answer to this question. Yeah, that is basically the answer to this question. So, yeah, so we've done one part of the question which says we should determine the linear momentum. Now we're going to the second part of the question that says we should determine the kinetic energy, E sub k. Now, again, this question is from the Physical Chemistry Atkins 11th edition textbook, and it's important for you to know that the formula for determining kinetic energy when you're dealing with free motion, and in this case, translational motion, the kinetic energy of the electron that we're dealing with is k squared is k squared h hash squared divided by 2m, where we already know what k is because we've been given it. We know that to be 3 divided by nanometers, or 3 divided by 1 times 10 to the power of negative 9 meters. Okay. We know what H hash is. We know that to be 1.0546 times 10 raised to the power of negative 34 joule seconds. And we know M to be mass, right? And you're going to be wondering, mass of what? Well, let's go back to the question. We're told that we're dealing with an electron, mass of the free electron. And the mass of an electron, for those of you who have done Gen Chem and some part of physics, this is not be hard for you. The mass of an electron is just simply 9.109, okay, times 10 raised to the power of negative 31 kilograms. And again, you can call it 9.1094, whatever you want to call it, times 10 raised to the power of negative 31 kilograms. So this is all the values you need. You already have your K, you have your H, you have your M. You can just simply substitute. But before we go ahead to substitute, let's not forget that our H hash here, H hash, I already explained to you guys, joules is the same thing as kilogram meter squared per second squared. So we're going to rewrite our H hash in the proper units and go from joules to kilogram meter squared per second square. And of course, we have the seconds here. We're not going to forget that. So I'm going to rewrite H to be 1.0546, okay, times 10 raised to the power of negative 34 kilogram meters squared per second squared. And let's not forget this here, which is a second. So we're just going to put that here. Okay. Yeah. Now we can simply substitute. E sub k is equal to 3, 1 times 10 raised to the power of negative 9 meters all squared multiplied by H hash squared, which is just 1.0546 times 10 raised to the power of negative 34 kilogram meters squared per second squared. Let's not forget the seconds since it's joule seconds. So let's not forget that one. And then all of this is squared as well because it's H slash squared. So divided by 2m divided by 2 times 9.109 times 10 raised to the power of negative 31 kilograms. So that is basically this. So E sub k, kinetic energy, will just be to just do the calculations and that's it. So 3 divided by 1 times 10 raised to the power of negative 9. 3 squared is just simply 9. Okay. And 1 times 10 raised to the power of negative 9 all squared is just simply 1 times 10 raised to the power of negative 18. And then, of course, meter will be meter squared here. So that's that. And then, of course, this one, 1.0546 times 10 raised to the power of negative 34 kilogram meter squared per second squared divided by seconds. Again, let me cancel out this 2 here, cancel out this second here. So anyways, 1.0546 times 10 to the power of negative 34 all squared is going to give you 1.1122 times 10 raised to the power of negative 68 kilogram. Okay. So kilogram squared, okay, meter squared squared, or meter squared times meter squared is just meter raised to the power of 4. And then we just have 1 second here. We just have 1 second here. So seconds squared is just seconds. Please pay attention to this. This is the part of the chemistry that requires a lot of breakdown of information and patience. If you just solve anyhow, you're going to mess your work up. That's just the truth. You're going to mess it up. Uh-huh. Anyways, 2 times 9.1094, or yeah, times 10 to the power of negative 31 kilograms is going to give you 1.82188 times 10 raised to the power of negative 30 kilograms. So, anyways, let's cancel everything out. Cancel out the meters, cancel out meters squared, and cancel out from meter raised to the power of 4 to meter squared here. Cancel out the kilograms, cancel out the square from kilograms. So, yeah, you do that already. So you've canceled all what you need to cancel out. By the way, sorry, I made a mistake here. This seconds here, when you square it, you have seconds squared. So yeah, we've canceled everything out. We've canceled out the kilograms, we've canceled out the meters. So you end up with 1 kilogram up top and 2 meters. And then of course you've canceled out the other ones. So rewrite this one. 9 E sub k ends up becoming 9 times 10 raised to the power of 18, okay? Because we brought this 10 raised to the power of negative 18 up, times 1.1122 times 10 raised to the power of negative 68 kilogram meter squared per second squared, divided by 1.82188 times 10 raised to the power of negative 30. So, of course, we input this information in our calculator, we end up getting E sub k to be 9 times 10 to the power of 18 times 1.1122 times 10 to the power of negative 68 would end up giving you 1.00098 times 10 to the power of negative 49 divided by 1.82188 times 10 to the power of negative 30. So that's kilogram meter squared per second squared. So E sub k is 5.49215 times 10 raised to the power of negative 20 kilogram meters squared per second squared. So that's basically the answer to this. This is basically the answer to this question, where we're told to find the kinetic energy, and we see that our unit is correct because the unit kilogram meter square per second square is the SI unit for energy, which we can simply write as joules. But I also wanted to mention something. While we've done our work nice, we have to remember that we are chemists and we have to put our work in the proper number of significant figures. And if we go back to our question, we see that the lowest number of significant figures we're given is 1. So we have to round this up or approximate this to one significant figure. So that would be E sub k is going to end up being 5 times 10 raised to the power of negative 20 joules. So this is basically the answer to the kinetic energy of a free electron. I have another question like this that I've done on my channel, so make sure you guys check it out. If you're in any way, shape, or form confused about what I've done, watch that video and rewatch this video. So I wish you guys all the very best. If you have any questions, suggestions, concerns of how I can improve this channel so that anytime you come in, you leave much better than how you came, please put everything that you would request in the comment section. I wish you guys all the very best. I also wanted to mention that if you're a student struggling in any of your STEM related courses, whether you're in middle school, high school, college, I am the tutor for you. I help students succeed in all their STEM related courses as well as mentor them in all the different aspects of academia in order for them to be the best version of themselves. And if you just want to know a little bit more about my services, email me at shuhabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.